Hello wonderful person, this is Anton, and today we're going to discuss some really intriguing propositions in regards to the famous Kardashev scale, the method proposed by a Soviet astronomer Nikolai Kardashev that tries to measure the level of civilization, and specifically its technological advancement, based on the total amount of energy the civilization is able to harness. With this proposition dividing all civilizations into three separate types, type 1, 2, and 3, or the planetary civilization that's eventually able to harness the energy of the entire planet, equivalent to about 10 to the power of 16 watts, the stellar civilization that increases this output by approximately 10 billion times, and can basically start building structures like the Dyson spheres, and the last type, the galactic civilization, whose output is now 10 to the power of 36 watts, and they can basically harness the energy of the entire galaxy. And for humanity, the assumption is that we're still somewhere below 1, or basically, we're roughly around 0.7 on that Kardashev scale. But today we're going to discuss a few studies that kind of create a fundamental shift in the way we measure all of this, and in the way we think about the idea of energy production and energy consumption, at least when it comes to civilizations. With the several recent studies you can find in the description, in essence showing us that this old way of thinking from 1964 does have a major problem, something that at least one researcher is now referring to as Kardashev's conundrum. And so let's talk about these studies and these new reinterpretations of this concept, linking some things that you might really not expect. Bitcoin, artificial intelligence, and the fundamental laws of thermodynamics and heat. And so to understand these concepts and what these studies are proposing, let's first discuss some of the initial assumptions by Nikolai Kardashev, once again from 1964. And let's actually put a face on that name. And so this is what he looked like before he passed away. And well, his assumption was that civilization's energy would actually grow at a steady 1% per year. And based on that prediction, he assumed that we are going to reach type 2 status, or basically control the entire solar system, in approximately 3,200 years. But there is a problem with that proposition and this assumption. And that's because when scientists recently looked at 60 years of real-world energy data, they found that this 1% growth model is an extremely poor fit. In fact, the actual growth was closer to 2%, but also fluctuated quite a lot on certain black swan events. For example, the year when COVID started. And moreover, if you try to fit the current progress into a simple linear model, or basically you assume that the energy increase is going to be linear, here the prediction really makes no sense. It would actually take us 1.6 quadrillion years just to reach type 2 status. This is longer than the sun will ever exist. And well, in essence, this is the conundrum. The old way of measuring progress, just looking at how many watts we create, does not seem to work. And that's because in this case, these assumptions do not account for quality of energy production. The original scale only measures quantity, how many watts, not what we do with it, and not how it was produced. And so to solve this, in this one study, researchers propose the new Kardashev-Sagan-Nakamoto model. With the name actually being just a little bit funny because, well, we have Kardashev, then we have Sagan, obviously named after Carl Sagan, specifically after the Sagan's information axiom, that argued that civilization advancement must also be quantified by its information richness and its ability to transmit complex data structures, or basically how well and how fast we can communicate. And Nakamoto is the mysterious Satoshi Nakamoto, creator of Bitcoin. And it's actually the use of Bitcoin as this yardstick that's somewhat intriguing here. Okay, before you click away, this is not a crypto video, let's actually talk about why Bitcoin was chosen. Because here it's actually used as a really intriguing scientific measurement. And that's because Bitcoin network uses what's known as a hash rate, and it provides the only global publicly auditable and unforgeable measure of so-called proof-of-work computation. Or in other words, it provides us with extremely accurate measurements of energy to information conversion. And so here, the researcher behind the study proposes dividing global energy production by the Bitcoin network's hash rate in order to get a new hypothetical unit referred to as Karnac, basically joules per hash. And so here Bitcoin network represents a measurable thermodynamic anchor for this idea of computational work that basically Carl Sagan was talking about back in 1973. And in this case, by analyzing data from 2009 to 2024, the paper definitively shows that while energy production around the planet increased by a factor of 4, the Karnac unit that he creates in the study increased by 14 orders of magnitude, or approximately 100 trillion. And that's because Bitcoin mining started with relatively weak CPUs, but now uses extremely advanced application-specific integrated circuits that are essentially used for mining Bitcoin, which is a fancy way of saying trying to break cryptographic codes extremely fast. And that means that in just the last 15 years, we dramatically improved our efficiency in turning energy into organized information, at least in that one particular example involving Bitcoin. But to resolve these propositions by Kardashev that no longer make sense, here the paper synthesizes concepts from astrophysics, computing, and thermodynamics, and also proposes a measurable goal. It's actually referred to as the Landauer's limit, or the Landauer's principle, which physically establishes a bridge between physical and digital world. And this is a fundamental physical law that tries to find the minimum amount of energy inside a computing device that it must dissipate as heat in order to change one bit of information. Or just to rephrase this, when you erase a single bit, or when you change a 1 into a 0, you essentially force it into a new known state. And this creates a kind of an entropy transfer that then has to satisfy the second law of thermodynamics. This lost entropy cannot just vanish, it must be exported into the environment and become heat, with this heat then being released into the surroundings. Now, originally this was proposed by Rolf Landauer back in 1961, and he essentially used this to prove that information is physical and does affect classical thermodynamics. But because back then, and even more recently, computers were extremely inefficient, this was actually seen as purely theoretical, because in this case, they would often dissipate billions of times more heat than this limit proposed. In other words, actual computers were never even close to this limit just because of heat inefficiency. But as modern silicon transistors started to shrink and become more dense, power dissipation has also become the primary bottleneck. And while we're still a few billion times above this limit, this gap is actually closing, with this study proposing that a true Type 2 civilization is not just the one that burns a lot of energy, but it's really the one that becomes so efficient that it finally reaches this Landauer's limit, the absolute physical minimum of energy required in order to process one bit of information. And at this point, information processing becomes so efficient that at room temperatures, this limit becomes very, very small. Approximately 3 times 10 to the power of minus 21 joules, or 0.018 electron volts. And so the Type 2 civilization, according to these new propositions, is not the civilization that can build a Dyson sphere. It's a civilization that has such an efficient information processing network that the information barely generates any heat and can use extremely small amounts of energy to conduct ridiculous amounts of calculations. And it's this efficiency that now becomes really important when talking about the next study. Because additional studies have now started to speculate what's going to happen to our society and our civilization as we start adopting artificial intelligence even more. And that's because the sheer speed of expansion in this case, once again, is way beyond anything Kardashev predicted. Historically, the energy demand usually grew pretty slowly, but with this AI boom, the requirements are now decoupling from traditional economic trends. With this research, you can find in the description, essentially suggesting that even though the general energy use increased by about 2%, the AI demand is growing electricity demands by staggering 15% per year, which is going to be unsustainable if it continues for several years. As a matter of fact, by 2050, it means that AI energy consumption is going to equal the rest of the world. With this acceleration now also creating a kind of a new problem, the Kelvin limit. Here, even if we create more energy and even super clean energy, such as the hydrogen fusion, due to laws of thermodynamics, it means that every bit of energy is still going to become heat. And that means that we're not actually going to run out of fuel, and instead, we're going to generate so much waste heat that the planet will potentially boil in just 67 years. Assuming, of course, that 15% per year acceleration. And so this continuous growth of 15% is completely unsustainable. And in that sense, this AI craze also creates a problem for our ability to one day become that Type 2 civilization. Because first of all, this introduces a kind of a decoupling from previous models, with the energy requirements suddenly becoming much larger, and the information processing not actually being efficient enough. And it also creates a major limit on resources that our planet can only sustain for a few more decades, which is why this study creates a kind of a speculative progression that's slightly different from that first study, or basically the progression of energy expansion based on the AI growth models. This is basically how long it takes to exhaust various thresholds. And while here, based on this 15% per year growth, the traditional resources such as fossil fuels and uranium are going to be exhausted in just a decade. And even if humanity manages to unlock perfect nuclear fusion, for example by maybe using AI to help us, even using all the deuterium available in the oceans, the sheer volume of energy demand is going to deplete the fuel stock and boil the oceans in 67 years. And so if AI continues to grow, we basically have to become interplanetary, or we have to achieve that Kardashev Type 2 scale pretty fast. And that means that this expanded intelligence must now find a way to capture the energy of the sun and to physically build some kind of a Dyson sphere in order not to run out of fuel. In other words, the conclusion from this paper is that the AI's rapid development and advances are now forcing us to confront physical limits of the planet, and actually much sooner than we anticipated. And so what we once thought might take hundreds or even thousands of years, because of this sudden growth of AI, has now been compressed into mere decades. Assuming of course it continues and the AI bubble doesn't pop, which it might, pretty soon. Although in this case, based on these studies, it actually might tell us a little bit more about this idea of great filter. Or basically the main reason we don't seem to see other alien species with a lot of Dyson spheres exploring the galaxy. And that's because maybe this transition from burning fuel to mastering information and creating these super intelligent AI systems may be either extremely difficult and results in a planetary collapse, or a truly advanced Type 2 civilization might not be a giant glowing factory and instead become extremely efficient, silent, and barely visible information processor, basically sitting at that Landauer limit. In other words, they're just invisible to us because they've become so ridiculously good. But for us, for humanity, we now find ourselves at a kind of a crossroads, because this might be the most volatile part of this journey, or a kind of a gateway to this potential great filter. Our artificial intelligence information engine seems to be growing faster than our ability to cool the planet. And our current success depends on shifting our focus from just using more power to actually learning from Bitcoin and processing information much more efficiently without using as much energy. Okay, well, on that note, this was of course more speculative and more informational, and we obviously have no idea what's going to happen in the next few decades. But it's still kind of exciting to explore these Kardashev scale ideas and talk about why we don't really see anyone out there, the Fermi paradox. Once there are some additional studies, we'll talk about this in some of the future videos. Until then, thank you for watching, subscribe, come back tomorrow to learn something else, support the channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining a channel membership that grants you early access. You can also support this channel by buying a Wonderful Person t-shirt in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.